I'm going to show that a function f is continuous if and only if it is continuous at every point x in x. So I've set up a preliminary template for this proof, where first we're going to go through the proof of a statement that is required to prove the main statement. So here we have part A. The statement is that if U is, also you have a topological space X, and if U is a subset of X, and if that is open, well, if that's given, then it's a neighborhood of every element of itself, and the other way is true as well. If U is a neighborhood of every element of itself, then it is open. So let's show this in both directions. So this way is almost vacuously true. We just have to basically state the facts of the definition and we'll prove the result. So let U in X be open. So what we want to show is that this set U is a neighborhood of every element of itself. So we want to show that U contains if it's a neighborhood of every element of itself, it contains an open set. We can call it some other letter with all those elements U living inside V as well. So show U contains an open set V, let's call it, with every element of U, or capital U, let's call it little u here, living inside the open set V. So that is V in U open with U in V. Well, this is, as I said earlier, vacuously true by just taking V to be the set U itself. And since U is an open set, the neighborhood contains, we've shown that the neighborhood contains an open set, and it's just itself. Since U is open, we're done with that direction. So for the other direction, so we want to show that if U is a neighborhood of every element of itself, then it must be open. So let's just call U, let's say U lives inside X, and we assume that U is a neighborhood. So I'm just going to abbreviate the word neighborhood because we're going to be using it a few times. So assume U is the neighborhood of every element of itself. I think I might need more space, so I'll just shift this down. So if, let's say an element X lives in U, then U would contain some open neighborhood of a point X. So let's call it V of X, some open neighborhood V of X, because we're assuming that U is a neighborhood of every element of itself. Right? So what we can do with all these neighborhoods of the points X in U, we can take their union. So if we're going to take the union of all these open neighborhoods or these open sets, because all of them are contained in U, and we're taking the union of all of them, then we must have that the set U itself must be the union of all those open neighborhoods. So we have U would be the union of all those neighborhoods where X lives inside U. And what happens if we're taking the union of open sets? Well, we're going to get the resulting set is an open set, and that, I guess, requires a separate proof, but we're not going to go through it here. So we're just going to use the fact that the union of opens is open. So we've constructed our U. So U is open, which was what we wanted to show. From here, we get that U is open. So that was not too difficult. We're going to move to part B, which is the main statement of this video. Here we go. So we have a function between two topological spaces X and Y. So f from X to Y. Here I've written down a couple definitions that would be necessary to go ahead with the proof. So the first definition relates to continuity at a particular point X. So given any X in X, we say that the function f is continuous at that point X if the inverse image, and this is the notation for the inverse image, not the inverse function, I guess. So yeah, we are working in topological space. So the inverse image of n, so where n is a neighborhood, so inverse image of n of every neighborhood n of f of x is a neighborhood of x. So it maps back to a neighborhood of x. So if it does that for a point x, it's continuous at that point. The second definition relates to, I guess, a more, so that was a local property. This one would be more of a global property about the function. So we're saying that f is continuous if any open v in our codomain y, the inverse image of v is an open subset of x. So that's continuity of the entire function. So one reasonable thing to assume is that, well, if the function's continuous at every point x, then we just call it a continuous function, and vice versa. So if we have a continuous function, then it's reasonable to conclude that from that definition we have continuity at each of those points x in capital X. But because of the way we've constructed our definitions, it's not an immediate result. We have to prove it. So what we're going to do first is, so it's an if and only if statement. We have to show one direction first. So let's suppose that our function from x to y is continuous. So what we want to show eventually is that it's continuous at every x in x. So if our function is continuous, then let's, I guess, just use the definition of continuity of a function. Then for any open so V in our codomain Y, the inverse image of V is open in X. So we have this. So let's take a point X in X. So let X be in X, which is a reasonable thing to do, and we want to show that it's continuous for all points X in X. And then obviously then f of X is an element of Y. So we're going to have some neighborhood of f of X. We're going to map, so we're mapping from X, map F to f of X. That's also a point in Y. There's going to be a neighborhood around that, closed or open, doesn't really matter for now. So we're just going to call it, it's just a neighborhood. So let n of f of X, this is kind of some strange notation, but I'm going to use it anyway. So let n of f of X be a neighborhood of f of X. So if this thing here is a neighborhood of f of X, by definition of neighborhood, it contains an open set containing that point f of X. So then n of f of X contains an open, say, V. So that's our open set that it contains, and obviously f of X lives inside here. So now the inverse image, so we're going to take the inverse image of the open set V is an open neighborhood of X. Well, why is it an open neighborhood of X? Well, because of our assumption that F is continuous. We're mapping back, we're taking the pre-image, or the inverse image, and it's going to be open in the domain. So the inverse image of V is an open neighborhood of X. So we have a sense the inverse image of V. Well, that's going to be a subset of the inverse image of n of f of x, because f is continuous, and this is true for all x in x, right? Because x was chosen arbitrarily. So then f inverse of n of f of x is an open neighborhood or no, not open neighborhood, doesn't matter. I think it shouldn't matter. Yeah, so then f inverse n of x is neighborhood of x for all x in x. Yeah, so yeah, it shouldn't matter that it's open, because we just want every neighborhood, not necessarily open. So hence f is continuous, and this is definition of continuity. Continuous at every x in x. Right. So that's one direction. Other direction. Let's look at the statement. So we want to suppose that f is continuous at every x. Suppose f is continuous at every x in x. So if, remember f goes from x to y, so if, let's take a subset of y, v in y is open, then the preimage is a neighborhood of every element of itself. Right, this comes straight from this definition of continuity at point x. It's a neighborhood of every point of itself. So what we have as well, so now we're going to rely on our first bit, or part A. So if we're going to use this direction here, so if we have like a set U, and it's a neighborhood of every element of itself, then that set must be an open set, right? So we use that fact. So from part A, well, this is the set where we're talking about, the inverse image of V must be open as well. Well, we're mapping, so we have open sets. So if we're looking at, where are we? Yeah, we want to show that F is continuous. So we're only taking open sets in Y, showing that its pre-image is open in X. So we took an arbitrary open in Y, took its pre-image. We know it's a neighborhood of every element of itself, because the function is continuous at every X in X. And from part A, we show that its pre-image must be open as well. Well, that's the definition of continuity of the entire function. So F is continuous.